Hi there, Dr. Huckabee here. This is another lecture that I took from last semester on Chapter 3. It's on acids and bases and using a qualitative method to determine which acid is the strongest. Please enjoy. And as always, here is your to-do list for this lecture. Okay, so your to-do list is to do the homework 3, work as many of the Chapter 3 problems as you can, finish reading Chapter 3 if you can, so that you can do all the Chapter 3 problems. And don't forget, we have an exam coming up September 15th. It's in 2 weeks from the time this lecture is posted to Canvas for you to view. Please contact me again if you have an academic conflict, if you need any accommodation, or if you're having technology issues. And I wish you all the best.
You can see here kind of the silly first slide of things to think about before class. It might seem a little strange, but all of you already know enough organic chemistry and basic chemistry knowledge to understand a very complex problem like ocean acidification. Because even though you don't know all the marine biology types of considerations that go into that, what you can already know is that CO2 can dissolve into water, become sodium bicarbonate, which then can be utilized by marine life at certain pHs to make very strong shells. And that's how we get our tasty shellfish, our coral reefs, things like this. Unfortunately, if you have too much carbonic acid, then you can move the equilibrium of this reaction to end up having more acid than you need, which shifts the equilibrium away from this very nice, oh, where's my mouse? It's gone. There it is. Which shifts the equilibrium away from bicarbonate towards carbonate ions, which leaves you with deformed shellfish, and who knows what happens to all our tasty foods and beautiful coral reefs. All right, so again, just to kind of touch on this idea of the delocalization of pi electrons, if you have two things here, either assuming they are sp3 or sp2, the sp3 electron configuration would look like this, where you had a localized pi orbital and the sp3 bonding to that C double bonded Y there, which would give you kind of a picture of those three bonds like this, where you would have the two pi bond, or the two p orbitals that make up a pi bond kind of by themselves with the same phases, and then you would have the lone pair kind of pointing away from them, okay? But if you instead assume that they are sp2, this is not to scale, but I hope that you notice the big difference in energy on these. Remember, energy always increases up, and as chemists, we want everything to be as low as possible. Okay? So here, by assuming that they're sp2 instead, when we mix those orbitals, we gain a huge amount of energy on the right side in the most stable orbital. And because of that stabilization, we can see that across all three atoms, those p orbitals want to be in the same phase, want to be overlapping and in conjugation. All right, so that's kind of our Chapter 2 review, thinking about the homework. Now I want to go just a little bit of review from Chapter 3 because it was pretty clear last week that I was not explaining this acid-base concept very well and explaining equilibrium very well. So I want to go back just really quick and talk a little bit more about KEQ and KA, because I think that is really where we can all understand this idea of picking aside reactants or products, and where we can be able to do that a lot better. So let's think about first, go back all the way to Gem Chem to Ka. Remember, that's the equilibrium constant for acid-base reactions. All right, and let's take any acid-base reaction. So we have H3O plus and A minus over HA. And remember, this is for any reaction that has the structure HA goes to H3O plus plus A minus. So this is for an acid dissociating into two things with the help of water, right? But we can actually turn this into a much more universal, generalized equation that can deal with any reaction if we instead change it to be, that's the other black one. If we instead go from Ka, the acidity equilibrium constant, to an equilibrium to an overall equilibrium constant. And this is going to allow us to think about reactions that have the form A plus B in equilibrium with C plus D. And that's going to be important because maybe we're not always in water, or maybe the things we're talking about aren't always water. So that means whenever we think about what the equilibrium constant is going to be, we're going to have four terms, which is going to be the concentration of C times the concentration of D over A times B. Okay? Oh, this is fun. I forgot about this. Okay, let me see if I can turn these lights back on. Because this happened the first day, and that really threw me, but I am prepared this time. Okay, so if I turn on minimal dimming, there we go. All right, is that still okay? Everybody can see? Great. Feels so good to be ready for that. All right, so this is not a math class, but I want to introduce to you guys a little bit of functional analysis, just a very teensy bit. What I want you to see in this fraction is that as the numbers in the numerator get bigger and bigger and bigger, KEQ also gets bigger, right? Like, for instance, if you had 1 over 1 versus 4 over 1 versus 8 over 1. You see how KEQ is getting bigger as the denominator is staying the same and the numerator is increasing? Now, also remember, if the denominator increases while the numerator stays the same, the number actually gets smaller, right? So in this way, we'll end up with a number, KEQ, that is either greater than 1 or less than 1. If KEQ is greater than 1, what's favored? Sorry, I might have heard it. Products, there we go. All right. If KEQ is greater than 1, products are favored. And if KEQ is less than 1, reactants are favored. Okay, so practically that's telling you in your reaction, as the concentration of products goes up, the equilibrium constant also goes up. Okay, does that make sense? It's a way to talk about what reactions are doing, no matter what reaction it is. So, if you remember from the very last bit of last week, I gave you an explosive reaction that was butyl anion plus some poor organic acid gives you butane plus the anion alcohol. And do you remember that the video? It was just fire coming out of the syringe, right? And that's because in this case, KEQ is much greater than 1. Because the base, the negatively charged carbanion, is not stable at all. If it comes into contact with a proton, it will just take it. So that means essentially the products side of the reaction here is infinity, and this is basically 0, as 0 as it can be. So this is a quick way to see a video of something on fire and bring it back directly to what is actually happening in this reaction. And that's a very easy example, but it's the exact type of thing that we're going to be doing over and over in this chapter, is thinking about where is KEQ and what does that mean for how far the reaction is going. Okay, great. And then one other small example that we can draw is something that's a little less apparent, but in this case, if we have imidazole and we add in dimethylamine, and we look at its equilibrium, we can see that the products would be this protonated imidazolium plus a deprotonated dimethylamine. And so the question to all of you is, which conjugate base is more stable? Right? Oh, I forgot some lone pairs. Okay. So first, what is a conjugate base? On the left side, is this the conjugate base? Any head nodding, shaking? I'm seeing some shaking. Is this the conjugate base? Ooh, no. So there isn't a conjugate base. Is there a conjugate base? Yeah, there is. Where's the conjugate base? Is it this one? Yes. This is the conjugate base. Well, this is the base overall of the reaction, the imidazole, because the imidazole in this reaction is taking the hydrogen and the electrons are going away. And it is the conjugate base of this protonated imidazole that is the conjugate acid of the base that we're using. So it's base, conjugate acid, which makes the dimethylamine what? The acid. Right, exactly. So it's the acid and makes this the conjugate base. What do you think is more stable? Positively charged nitrogen or negatively charged nitrogen? Raise your hands for negatively charged. Okay, we got some. Raise your hands for positively charged. Okay, we've got some as well. Lots of attentions. How many times have we run into positively charged nitrogens already? A few times, right? How many times have we run into pretty stable negatively charged nitrogens? Not often. So here, the positively charged nitrogen is actually the more stable one in these two. And one way you can know that is because its conjugate base, this imidazole, is more stable than the negatively charged nitrogen. Because this basic nitrogen site is neutral, and this one is negatively charged. So when you're comparing the two basic sites, if one is neutral, it's probably more stable than the negatively charged one. I really did not explain that first part well, but hopefully the last part stuck a little bit. Okay, that's a lead into where we're going. Don't worry if this didn't stick, because we're going to go through it much more in detail now. And I'm hoping we can get through today what I want to. We will see. We're a little behind. All right. Okay, so that's over here. Great. All right, so the real star of the show in Chapter 3 is a simple mnemonic we're going to use to do qualitative analysis of acid-base reactions. Because if you remember, on Thursday, we did quantitative, right? Where we saw the molecules, we looked at the Evans pKa table, and we said, this one has a lower pKa, so it's more acidic, right? This time, we're going to learn how to do that without the table. So from now on, just assume the table does not exist for our intents and purposes. So now, how do you look at a reaction, say, like this, where you have a base, oops, forget that was over there, and an acid, so how could you look at these and know without the table? That's the question. So this is going to be where we start. So the mnemonic we're going to use, if you've looked in your book on Chapter 3, you probably know this already, but it's called ARIO. ARIO, if you will. And each of these stands for different things. A stands for atom, R for resonance, I for induction, and O for orbital. Okay, we're going to go through each of them and talk about exactly what they mean and give you plenty of examples so that at the end you can be a wizard at identifying which things have the most stable conjugate base. Because the key in qualitative analysis of reactions is to find the most stable conjugate base. The reason why that's the biggest thing to do is because a more stable conjugate base means a stronger conjugate acid. Does that make sense? Let me say it again. A stronger acid means a weaker conjugate base, right? Do you remember from our example of HCl? HCl dissociating completely to give H plus Cl minus. And this happens because Cl minus is a very bad base that basically doesn't do anything. It's super stable. That's because HCl is such a good acid. So, when we're looking at reactions like these, finding the most stable conjugate bases being the basic ones, like this, and like this, because they use their lone pairs to take the hydrogens, right? So finding the most stable conjugate base tells you where the acid, or where the strongest acid is. And that tells you which side is favored. So if you find the most stable conjugate base, you know which side the reaction happened on. So the first one we'll look at is atom. And basically what that says is, follow electronegativity rules, and the atoms to the right are going to be the most acidic, but atoms going down are going to be the most acidic. So this means that nitrogen atoms have more acidic protons than carbon, oxygen than nitrogen, fluorine than oxygen. But sulfur has more acidic protons than oxygen does, which means sulfur makes the more stable conjugate base than oxygen. So if we know that, let's use red, if we know that sulfur is the more stable conjugate base, that means this is going to be the side that is preferred. Why? Because that means the thiol was the most acidic, and this reaction is going to happen a lot more. Does that make any more sense? Maybe not. Maybe. All right, let's keep going. The next one we'll look at is resonance. And resonance essentially says that if there is some resonance stabilization in the conjugate base, then that atom will be more stable. And as an example of this, let's look at these two molecules. Let's look at all right, so here we have propanol, C3H3578O, and propanoic acid, H356, or yeah, 356, C3H6O2. There we are. I don't know where I'm at today. C3H6O2. So then, if we're going to find out what is the most stable conjugate base by resonance, it really makes sense just to go ahead and draw the conjugate base of these molecules, right? So if we draw the conjugate base of these guys, let's just move this here. There we are. Whew. Yeah, that should, oh, here we go. There we are. So if we draw their conjugate bases, the negative, there we are, and there we go. Those are the two conjugate base structures, right? Both of them are negatively charged because they just gave up their proton to some stronger base. Okay, which one of these has resonance stabilization? Can you already see it? Hopefully, you can see that it's the second one that has a resonance stabilization. To make that second molecule there. Okay, so because the negative charge that you make upon forming a conjugate base is delocalized around the whole or around those three atoms here, the one carbon and the two oxygens, that molecule is going to be more stable. The conjugate base is more stable, so that means the acid is stronger. Okay, imagine that there are two people who are making, who have a business. One person A, is making this thing, whatever that is. All right, person B, he uses this thing to make, I don't know, a plus sign. Whatever it is, it doesn't. Oh, it's up, right, yeah. There we go. So I kind of think about it as this internal struggle. Like the proton is the thing that they're fighting over. One wants to make something, and the other uses that product to make something else. So they're fighting over resources in a reaction. And when you're looking at which acid-base product is going to be the most favored, you are looking at who is doing their part of the reaction faster. And you know that from the conjugate base, because if the conjugate base is more stable, the reaction went faster and the acid is stronger. I'm going to keep saying it. It's going to be very boring because I'm going to keep saying the same thing over and over again. Conjugate base is more stable, acid is stronger. Yes? So the question was, does stable mean weaker in terms of basicity? And the answer is yes. So when I say stable, that means the base is weaker. Yes? It is, you will always get the right answer if you just think about conjugate bases. You can think about conjugate acids, but it gets a little more complicated. For a conjugate acid, I tell you what, we'll talk about conjugate acids in a minute with amines, but they're a special case, and mostly you never have to think about them for determining what a reaction is doing. So please, unless it's, how about this? If I'm asking you to find, what am I trying to say? If you're trying to gauge acidity, think about the base. Okay? You're always going to take an acidic molecule and first make the base so that you can draw conclusions from the base. Only think about that right now. All right, so that was atom and resonance, right? Those are the first two. The third one was called induction. Oh, wait, I forgot. Let's break up this very boring conjugate base talk with a little bit of OChem as a foreign language. So carboxylic acids that we just had on this DocCam are actually pretty cool molecules and ones that we interact with all the time in our lives. From vinegar, which is acetic acid, to formic acid, which we learned about last week with the ants, to butyric acid, which smells horrible It is just, it's actually vomit. It's really bad. To kidney stones, which hopefully none of us ever have to worry about, to even these amino acids here that are present in our bodies at huge amounts. Carboxylic acids are very important for basic life, and it's something that it's another small way that organic chemistry actually matters in our lives, much more so than just trying to think about conjugate bases. All right, but to go back to conjugate bases,